Today I shall discuss the different components of the galvanometer and the working principle of the galvanometer in this video. These are the magnified view of the components of a suspended coil galvanometer or Darsoval galvanometer. This is a fine insulated copper wire frame. This is wound on a metallic frame, not shown in this slide. I will show it in the next slide. There are several turns in this section. As the number of turns is increased, deflection will be increased. This is the phosphor bronze fiber with the help of which this rectangular copper coil is suspended. This rectangular insulated copper wire frame is placed inside the pole pieces of a permanent horseshoe type magnet. This is the north pole, this is south pole. This cylindrical cavity along with this cylinder of soft iron core ensures that the magnetic field in this cylindrical cavity in which coil moves, rotates, the lines of force are always perpendicular in any position of the deflected coil, are perpendicular to the perpendicular sides of the rectangular coil like this. Let us see the animation. As soon as coil rotates at any position of the rectangular coil, the magnetic field, the lines of force are radial, that is, they are perpendicular to the perpendicular sides of the rectangular coil, and it is uniform always. Here is the magnified view, so the gap in reality is very small. I will show it in the next slide. Some company uses one spring, one control spring instead of two control springs. But it is not important whether it is two springs or one spring. The main feature is that why the rectangular coil deflects when current passes through it. A needle is connected with the control spring. I will show it in the next slide. And this needle deflects, indicating the presence of the current in the circuit. The current from the circuit enters into the coil frame through this control spring. The one end of the control spring being connected with the coil frame, the current enters into this coil, and after rotating few rotations in the coil, it emerges through this phosphor bronze and the control spring to the circuit again. This cylindrical soft iron core, solid cylindrical soft iron core, is attached to the wall of the galvanometer case. The galvanometer case is shown in the next slide. All these components are placed inside this galvanometer box. So it is clear this is magnified view of the components. Naturally, the gap between the cylinder and the metallic frame, or the gap between the magnet pole pieces of the magnet and the coil, all are very small. Now as soon as I will switch on the circuit, that is, current will start to flow. Look, this is the direction of the current in this part of the frame, and this is the direction of the current in this frame. So current is flowing in this fashion. And I have already told you that Instead of two control spring, some company uses only one spring. But whether there is one spring or two springs, it doesn't matter. The target of this video is to understand the direction of the throw and how this throw occurs, the physics behind this throw. So concentrate about the theory. As soon as current flows through this part, according to Fleming's left-hand rule, this is the forefinger indicating the magnetic field from north to south. The middle finger indicates the direction of the current. So the thumb indicates the direction of the force in this part. But in this section, the direction of the current is opposite. So let us stop the animation. I have inverted the left hand. Now this is the direction of the current, this is the direction of the current. The direction of the magnetic field from north to south is same as before, but here the thumb is in this direction, so this part will experience a force along this direction. So the force in this part is along this direction and this direction. This part force is in this direction, in this direction. These two equal and opposite forces forms the deflecting torque in this direction. Due to the elasticity of the spring, this control spring rotates in the opposite direction, and it rotates until the controlling torque balances this deflecting torque. A needle is connected with this control spring, and look at the initial position when there is no current in the circuit. The needle is at zero position of the circular scale. The shadow of the coil is at zero position. Look, as soon as current starts to flow, the needle deflects to the point indicating mark 10. There are two marks indicating 10. That is, this indicates deflection in anticlockwise fashion or left hand, or this indicates right hand. So if direction of the current is reversed in this part, the coil will deflect in the opposite direction, and this needle will deflect it in this mark 10 position. So this is the shadow of the equilibrium position after deflection, after passing the current of the needle. So look, again stop the animation, initial position. This is the initial position when there is no current. Look at the movement of the spring as well as movement of the needle, the shadow of the needle in fact. Look, the shadow is now at mark 10. Another important point is that these two parts, horizontal parts of the metallic frame, that is rectangular coils, these horizontal parts, the current in these horizontal parts are parallel to the magnetic field. We know Biot-Savart's law, I dl cross B, dl being parallel to B, dl cross B is 0. So these two parallel components of the currents does not create any effect on the throw of the coil. So this is the physics behind the rotation of the coil. Stop the animation. Again, look at the direction of the rotation of the spring and the direction of the rotation of the frame. Look, they are in opposite direction, opposite to each other. This is rotating in this direction, this is rotating in this direction, controlling torque, and the coil is rotating in this direction, the deflecting torque. As soon as the controlling torque and deflecting torque are equal, the rotation ends at a point, say 10. We have not used any unit in this section because we are not interested about the amount of current. We are only interested whether there is current in the circuit or not. It only senses the existence of current. If a low resistance is connected in parallel with this circuit, it will be converted into ammeter or milliammeter. Then, if a known current of say 10 milliampere is passed and the deflection is at Mach 10, then it is 10 milliampere. If the graduation is increased, I have not increased the graduation, I have not shown any finer graduation in this case because the shadow of the marks will create a confusion in this region. So I have only indicated 10, 10 and 0. But in case of milliammeter, if we graduate this scale in finer divisions, if for a known current of 10 milliampere the deflection is 10, then it is 10 milliampere. If for an unknown current the coil is this needle, if it stops at position Mach 2, then it is 2 milliampere. So it can be converted into milliammeter or ammeter. Similarly, if we connect a high resistance in series with this galvanometer, it will be converted into voltmeter. In the similar fashion, if a known voltage of 10 volts say is connected across this circuit and the deflection is Mach 10, then it is 10 volt. Then it can be calibrated in this way, and a unknown current of 3 volts say can be measured when the deflection is at Mach 3. So this is the basic principle why the needle of a galvanometer deflects. I have just said a current of 10 volt. That is not true. Actually, what I want to say, if a current in any part of the circuit is such that voltage across that very part of the circuit is unknown, and if the deflection at that time is at Mach 4, then the unknown voltage is 4 volt. So calibrating the circuit in this way, with the help of voltmeter we can measure the unknown voltage in the